Boiling water. You'd think I'd have some sort of reason for starting off a video with boiling water. Hey guys, this is OC. Doing a video here, and you might think it has something to do with this boiling water. Well, it does, but not in the sense that you may think. Actually, what I'm interested in today is, well, I'm making tea right now. And so if I'm making tea, I was thinking, okay, I take this boiling water, and here, follow me along as I do this. So, if I was, amazing, great tea person, the next thing I would be doing is I would actually be using a kettle and doing this process. But what I'm going to do here is I'm going to take my teapot, okay, and you'd think it'd be nice and easy to just actually have a kettle here to do this, but I'm going to cheap this and use a funnel, and I'm going to pour this boiling water into my teapot. And so the question I was wondering to myself was, why do I use boiling water? Because if you think about it, you're extracting some of the tea out of the tea bag. Get a lot of that in there. Brewing tea. And so that tea is being extracted out of there and dissolving into the water. So the water is actually being the solvent in this system. And, ooh, you can see that. Remember, that white cloud is actually condensation. Don't forget that. Anyway, so, I have this tea in here. My gosh, shortbread tea. Smells good. So, I was wondering, at some point, does this thing reach a maximum amount of tea that could be dissolved? Because I see some people put in, like, 22 tea bags or like 10 tea bags. I put 8 in when I do iced tea and things like that. When I do this, I do 1 tea bag, but they always give me a certain ratio. So that got me to thinking, is there a limit to solubility? Can something only be so soluble? And if so, does changing the temperature actually have an effect on it? Let's go to the lab and find out.
Now we're in the lab. So to answer the question of solubility, and some terms we should know when dealing with solubility is, let's take a look at an example system in the lab. And let's see if we could play around with it and find out any more information about what we know about solubility and how it may change in different conditions. So we already know that we have solvents. Water, common solvent. If we're talking about a lot of, biological materials, we are talking water as our solvent. It's called a universal solvent. Alright, it's the thing that does the dissolving. It's going to take the materials that we put into it and it's going to break them apart because of intermolecular attractions. Things like hydrogen bonding, dipole-dipole. Not really so much the dispersion forces since they're rather weak here. Or ion-dipole forces, depending if we have an ionic system. Water is going to be our solvent in our system today. And I measured out about 30 milliliters of that in here. Alright, so I pour that in to my beaker. All right. Now we're going to investigate an interesting salt today. Sodium acetate. It's a white powder, preservative. It's a common chemical used in a lot of your food materials. If you look on a lot of packaging of dried materials, you're probably going to see sodium acetate in a lot of these. All right. I got it out of a reagent bottle though, didn't get it out of any food. Okay. So we have fresh sodium acetate here. So what I'm going to do is, right now we have 0 grams of sodium acetate dissolved in this. Now, most solubilities commonly, especially in the real world, are expressed in grams of solute. This is a solute, the thing that's going to get dissolved. So whenever you dissolve something into something, that's a solute. Okay, the dissolvent, the solvent does the dissolving. All right, the solvent is dissolvent. A student told me that once. This is the solute. It's the thing getting dissolved. It's going to get essentially broken apart into different substances. It's not going to chemically change. It's only going to physically change, essentially speaking. Okay. So there's 0 grams of it dissolved in 30 grams of water right now. Remember, density of water is about 1 gram per milliliter. Within a reasonable assumption of value. So what I have here is I have a little sodium acetate, and I'm going to put it in here. All right. So I put that in there, and it's stirring because I have a magnetic stirrer hooked up to this. Okay, and what we notice is it dissolves. Okay, how do I know that? Well, if you look in it, The only white thing you see in there anymore is just the magnetic stir. No other powder in there. No powder in there at all. Okay? So there is some actually dissolved in here right now. So a solution in which I have some dissolved, but we can dissolve more. All right? And you might say, how do I know? I'll show you in a second how I know I can dissolve more. That I can dissolve more, this is called unsaturated. Right? An unsaturated solution. So if you put a little sugar in your tea in the morning, you put a little sugar in your breakfast cereal, you put a little sugar in some soda, use one of those cool soda streams or something like that, yeah, it's unsaturated. All right? The way you can test if it's unsaturated is a very simple test of, well, put a little more in. So I'll put a little more in. If the prior solution was unsaturated, then it could hold more. It was unsaturated. It means it could hold more. So if I put more in and it dissolves, it was unsaturated. So I let this sit here for a little bit, and again, still dissolved. All right. Sodium acetate has a relatively high solubility per 100 grams of water. All right. Now I only have 30 grams of water, so we could calculate the value. In fact, I'm going to show it to you right here. All right. So we have a max value that we can hold at a certain temperature. Okay. So what I could do now is, instead of being timid, I could just keep adding in. So let's just add in and add in. And as I'm adding in here, it dissolves rather fast. Do not confuse the speed of dissolving with whether it does dissolve or not. A common thing in chemistry that we talk about is, just because it will happen doesn't mean it happens fast. For instance, change in the political system. Not getting into politics, but change happens, not very fast. Just because something's going to happen doesn't mean it happens. A car will rust. Does that mean it's going to rust tomorrow? No. You don't buy a car and hopefully it doesn't just rust right out the bat. Okay. So I'm still pouring this in here. Stirring, stirring, stirring. Okay. And now it appears that I have some residual solid on the bottom. Now again, it could be because I haven't given it enough time, or it could have actually reached its max saturation. Okay? So there is a limit. Because if we think about those water molecules going around, they're going, wee, 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 pew, 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 and they're taking these little molecules and going, pew, 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 sorry, formula units, pew, pew, pulling them apart, and dissolving them, then there's only so much water there. There's only so many people that can handle it. So if you're like thinking about students who are doing homework, you can only throw so much homework. They can only absorb so much before they reach a limit, a solubility limit. And that's what we usually write down when we talk about solubility. The limit of its solubility, its saturated value. How much could actually get dissolved max? Okay? And what I have here now is I do have undissolved particulate. So I actually have crystalline material still in there that will not seem to dissolve. And again, I can prove that this is actually saturated, because if I add more, it just stirs around. That's all it does. So I'm saturated now. All right? So a substance, a solution I should say, that when we've reached the max amount that you can dissolve, that solution is saturated. And no matter whether I try to add more or not, the most amount that can be dissolved is dissolved, and no more will dissolve. Okay? So no matter what I do here, I can try to add more, because I just want to dissolve more. I want to really juice up my Kool-Aid and get lots of sugar in there. So you put a lot of sugar in there because that packet ain't enough. Well, there's only a max. Okay? You'd be surprised how much sugar can actually get dissolved. So I could pour all this in, and you can clearly see now it's just a white slurry of crud. Okay? It does not dissolve. All right? Remember, the kinetics of dissolving a sodium acetate is very fast. If it was going to dissolve, it would do it very fast. We'll talk about kinetics later on. But the basic idea is, if it was going to dissolve, it would have done it pretty much by now. Okay? So we can change solubility. A lot of substances, solid to liquid systems, solid, liquid, solvent, can have their solubility changed by increasing or decreasing in temperature. And generally it's a direct correlation. The hotter you get it, the more you can actually dissolve. If you think about that back to my homework analogy, if I make you a faster and better and stronger student, a student that can get around more, and you're working faster, you could attach yourself to these molecules better and these formula units and these salts and dissolve them. And the same thing generally is true. Not all substances. There are substances that don't change their solubility, and there are a few solids that don't actually dissolve. They actually dissolve less as we increase the temperature. But generally speaking, and that's how we like to talk, generally speaking, you want to make more dissolve, heat it up. So that's what I'm going to do. I'm going to heat the crap out of this system. Okay? And so we're going to let this sit here and heat for a little bit and see what happens. All right? So we're going to let this heat, and I'm going to let this record it so you can see what happens. All right? I'll see you in just a little bit. Okay. Hey, Woody, how did you get here? All right. We're getting to the point now where this is getting pretty hot. And what we're seeing now is I'm seeing that we have our solution is pretty well dissolved again. All right. It's heating up. I still have a little itty bitty bit of cloudiness, which will go away here shortly. But the sodium acetate is now dissolved in this system. Okay, which means I've raised the temperature enough so that I'm underneath the saturated amount that could be at this temperature. So the solubility of sodium acetate greatly increases as temperature goes up. So that means if I want to dissolve more of it, I heat it up. So technically, if you want more sugar in your Kool-Aid, drink hot Kool-Aid. Okay, you might say, well, obviously, because I can put the same amount of sugar in it, dissolves faster. Hey, whoa, 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 that's kinetics. Speed of dissolving does not mean it will dissolve. But the thing here is, I have now dissolved this to a point that I have more dissolved than I normally do. Okay? And we have no solid in here anymore. Okay? So we have a saturated solution of sodium acetate. All right? Now, if you turn the heat off and let this cool, with a lot of systems what would happen is, as you cool down, the temperature would lower, and after a while, got really clear now, and after a while, you would then hit the max solubility again because you'd be going backwards, and then you would hit at some point, it's too cold for that solvent to handle that solute at that temperature. So you would start to see crystallization take place. Sodium acetate is kind of neat because it exhibits the ability to actually stay dissolved, because it becomes like metastable, we call it. You can think of metastable as if you're a ball on the top of a mountain, right at the apex. And it's like, well, shouldn't the ball fall? But if you bounce it just right, it's not going to fall. But it's really not stable because, man, that one little oof, and it's gone. And it's going to go right down that hill. Okay? That's sort of what sodium acetate does. It gets to the point where it's like not precipitating out, not crystallizing out because it's above its solubility. What happens when it cools down is it gets metastable. It sort of stays dissolved. The water can't get around it and actually reattach itself to itself, so it can allow the sodium acetate crystals to reform. Essentially, you could think of this as the Mentos Diet Coke thing. There's no nucleation site. There's no initial site where it can actually nucleate and start to form that crystal in order to precipitate out. For sodium acetate, it's real key to have that nucleation site. Some things, it wouldn't matter. Some things, it would crystallize out no matter what. Okay? So, can that actually happen? Well, it can. And what I have here is, I have already prepared a system like that. This is a pre-prepared solution of sodium acetate, and it is supersaturated. You might look at it and say, how do you know it's supersaturated, OC? And I'll be like, well, because I said so. But if you want proof, as you should ask, I love it when you guys ask, how could I prove that this is supersaturated? Let's see. Okay, unsaturated, I put a crystal in. And what'd that do? Oh, right, it'll dissolve. Okay. Saturated, if I add another crystal when it's saturated, well, that crystal just stays there because it can't dissolve, okay? FYI, to say that dissolving still isn't happening, that you might want to watch that idea. Even in saturated, some of those crystals are still dissolving, but some of the ones that are in solution crystallize back out at the same speed. There's that equilibrium that goes on there. Anyway, so how could I test this? Well, why don't I put a crystal in here and see what happens? Okay, so I'm going to open this up. All right, let's see there. Now what I'm going to do is I'm going to take a little extra crystal. Remember I told you one of the problems of why sodium acetate is metastable is because it doesn't have that nucleation site. So if I provide a site for nucleation, maybe I can get the metastable state to be forced down to a stable state. And as you can see, a solid is forming. That is all the excess sodium acetate that was dissolved, precipitating or crystallizing out. Okay? And all of it just crystallized out. That's all the excess. There is still a little water in there. These are kind of damp-like crystals. And these damp crystals, why are they damp? Because there's still water in there. And that water is saturated with sodium acetate. So what's all this solid? That's the excess sodium acetate. Okay? You know, you can see a little bit of water still in there. But essentially, I have a solid now. Because that's all that extra sodium acetate that's not soluble at this temperature. Another interesting thing is, this is really warm right now, which tells us that crystallization is an exothermic process, generally speaking. And since it's exothermic, that means dissolving is endothermic. Well, we're going to learn about how we can favor processes like endothermic processes by heating them up, like I did to get this into that supersaturated state. And we could use this in hand warmers. All right? Reusable hand warmers are based off this same principle of precipitating out a supersaturated sodium acetate. Look up Easy Heat online, and I think that's a brand name, but that'll get you what you want. And you'll find hand warmers based off the sodium acetate setup. All right? And you can tell now, you know, I pretty much have a solid system. All right? So, those are your three different descriptions of a system and how temperature can affect solubility of solids. All right? So, take this and let's think about back to where we were when we started to ask this question. And so now we're back with a little more knowledge about solutions and solubility. So, when I drink this tea, which is amazing by the way, when I drink this tea, I know that there is some limit to the solubility. So I could put a ton of tea bags in there, but there's some limit to how much it can hold. And heating it up does allow more to be dissolved, generally speaking, and so that allows more tea to get dissolved. But unless it's one of those special systems like sodium acetate, it'll never become supersaturated, and I won't drink a little bit of my tea and suddenly I just get a solid stomach of tea. That won't happen, at least to my knowledge. So, what you should do now is grab yourself a nice cup of tea. I'm drinking shortbread. It's amazing. Oh, so good. Anyway, I'll see you guys here next time. This is OC. Talk to you guys later.